One of the characteristics that we talked about early on in the year is the idea of a function being continuous. And we treated it from a visual perspective of that a function is continuous if you can draw the whole function without lifting your pencil. And so when I look at the comparison just between two simple parent functions, x squared and 1 over x, we would say that the first is continuous, while the second is not continuous. But this really misses the point. In fact, the second function is continuous at every value except for 1. We say that when x equals 0, 1 over x has a discontinuity, and particularly an infinite discontinuity, because that's where the graph breaks. And so this idea of continuous versus not continuous was somewhat fuzzy. Right? We certainly grasped the idea of discontinuities well and understood the algebra of where they come from. But we can interpret continuity in terms of the limit definitions that we know. Right? There's a way to describe the difference between what happens in y equals x squared and what happens in y equals 1 over x, particularly that value x equals 0. So to start, we start with a basic definition, the definition of continuity at a particular value x equals c. Okay? So we say that a function f is continuous at x equals c if three things occur. 1, f of c exists, meaning that the height of the function exists at that point. 2, the limit as x approaches c of the function exists. And 3, the height of the function is equal to the limit as x approaches c of f of x. And these three pieces together should make sense for what causes us to be able to draw the graph from left to right. Because what this says is that as I approach, particularly the second part, right? As I approach c on the graph, the limit exists, and once I get to c, what happens? That limit is the same as the height of the graph. So for each point I approach, as I move from left to right, I actually get there. So it's a very simple definition of continuity. It fits within the new terminology that we've been developing. What it allows us to do is make a small distinction then for a graph like this. And we say, well, is this graph continuous at any values? Right? And the answer is, yeah, sure, this graph's continuous at all real numbers except for 0. Right? Or we could do the following intervals, minus infinity to 0, union 0 to infinity. Which brings us to the discussion of what does it mean to be continuous, not at a value, x equals c, but continuous on an interval, ab. Well, if we're going to be continuous on the interval ab, the following things must be true. So, if we just want to be continuous on the open interval AB, then all that matters is that for all C, which are in that interval, which are elements, that's not epsilon anymore, that's the elements of AB, right? F of x is continuous at C. So, if I want to talk about this rational function being continuous on the interval from 0 to infinity, right, I would just have to make sure that I was continuous at all values. Not at 0, though, right? We're not continuous at 0, but we don't include it. It's not included in the interval. Which just leaves the last question: what about an interval in which what if we wanted to include it? Right? What if we had a function where we wanted to include particular interval breaks, like the following? So, what if we want to be continuous on a closed interval? AB, which in this case, for this particular problem, that would be the interval from -3 to 3, this being half of a circle. Right? Well, this is a little bit different, and the reason it's a little bit different is if you think about being continuous, it means the limit has to exist at that particular value. Right? How do you get the limit to exist at b if you don't have, right, if this is b here, the very end, how do you convince yourself the limit exists if you don't have the right-hand side of the limit? The function stops there. So instead, we say the following. Again, we need to be f is continuous on AB. The second thing we can say is that f is continuous from the right, and we've done this before, at A, and this is just the idea of breaking down the limits from side to side, and f is continuous from the left at B. Alright, so this is another definition. We've had continuity before, but we wanted to put it in a framework that we understand, and then we're going to build on this in the next video.